Hi, thank you for joining our special interest group meeting today. My name is Binna. I'm an application engineer for offshore product. Today, I'm going to talk about the unique solutions MOSES has to design connectors. Let me start. As some of you may know, MOSES has an element named connectors. What the connectors do is, as indicated in the name, they connect objects together. As shown in the picture on the left, if we use it to connect the seabed and the vessel, it becomes mooring line. Same for the lifting slings. We can make a connection between the cargo and the vessel with the connector. So, these connectors allow the cargo and the vessel to communicate each other during the simulation. Another type of connector is thruster. If we look at the picture on the right here, it seems there is no connectors in the system. We cannot see blue lines here, but the thrusters for the dynamic positioning are connected to those points highlighted by red circles. So MOSES applies a thruster force to those points in time if the body goes beyond a specified range. Of course, MOSES has many more types of connectors, such as leg mating unit for float of analysis or generalized spring element to simulate their springs in time. But today, let me focus on the specific type of flexible connectors. They are mooring line, lifting slings, and thrusters. Because MOSES has special commands to design these types of connectors. They are available inside the connector design menu, and this menu is today's topic. First of all, let me explain the concept of the connector design menu. For example, as for the mooring analysis, we usually model a vessel and the mooring line and define some additional weight properties. Then run the analysis either in time or frequency domain. This is what we usually do. But before the analysis, at the very initial design stage, when we just started to build the analytical model, it is in question that what the pretension mooring line should have, or how many lines we need to get proper restoring force. There are two pictures on the left. If we look at the picture at the top here, we can notice that line has more tension than the line in the picture at the bottom here. For station keeping point of view, the line in the picture above looks better. But as we know, we also need to think about the line tensions and the forces at the anchor and ferried point. In this regard, the line in the picture at the bottom allows more motions but has less tensions. In real world, the shape of our catenary system is somewhere between them. So we need an additional information about mooring line itself to make a decision. Same for the lifting slings. If we look at the picture on the right here, the jacket is hanging in the air by the lifting slings. As you see, hook location of first two pictures from the left are different. And also, if we compare them with the first picture from the right, one of the slings are attached to the different point of the jacket. When you model the rigging system, location of the hook point and the joint the slings are attached to affect the tension in line. Here, we may think a parametric study to find an optimized sling configuration. However, if we perform the study by running the analysis with the whole system, this could be very time consuming. And furthermore, this may not what we want. What we need at this very initial design stage is not the final optimized one. In other words, what we need is a reasonably approximated value to start with. This is what connector design menu is intended for. A set of information from the connector design menu helps you to decide those values. Let me move on to the next page. 5 commands are available inside this connector design menu. As you see, 3 commands for the mooring line design and 2 commands for the sling and thruster design. Let me explain how these 5 commands can help us. For your reference, from now on, MOSES commands will be written in blue text, and as you see, their font is different with other regular text in black. Let's take a look at the commands table first. This command is for mooring line design. To issue this command, as you see, we need to enter the connector design menu, then write the command. One thing to note is that we need to specify the name of the line in the model, because this command is to investigate the characteristic of one line. Let's take a look at the picture. Here, point A is the anchor point, and the other end of the line on the vessel is the ferried point. Once this command is issued, MOSES only considers the vessel and one connector. As you see on the screen, the line is currently in slack, so we can expect there is no horizontal force at the ferried and anchor point. Then MOSES increment the horizontal distance between the ferried and anchor point with a specific step size until line tension exceeds the breaking tension. The picture at the top shows what MOSES computes at each step. As you see, it calculates the horizontal and vertical forces at the ferried and the anchor point, and the tension in line. And it also calculates the length of the line on the seabed and the height of the first connection if the line is segmented. This information provides us a really useful insight about the behavior of one mooring line. Let's take a look at the output of the command. Here's the output of the command. Horizontal forces at the ferried are reported. Then, line tensions, the horizontal and vertical force at the anchor are reported as a function of horizontal distance. Let's take a look at the table closely. First of all, in this second section, second column, the force is the horizontal force at the ferried, and this dF over dx is the ratio between the force change and the change of the horizontal distance. As we expect, the force and the ratio starts from almost zero and increases as the line stretches, then finally reaches the breaking tension specified. If we look at the lower part of the table, the line is on bottom is almost zero. So small change in horizontal distance causes large tension in line. For example, if we take a look at the last two, 1.5 feet difference causes additional 100 kips. Here, one thing to note is that we can say the horizontal force and the ratio are the restoring force and the stiffness of one line at that horizontal distance. So, through these two columns, we can get an idea of line stiffness and restoring force against the change of the catenary shape. In the next column here, the line tension is reported. Here, top tension is tension at the ferried, then ratio between the tension and the breaking tension is reported. For your reference, the breaking tension can be defined. Other sectional properties are specified. The vertical and horizontal forces at the anchor point is reported in the next column. One of the things useful is vertical pulling force. We can check how the forces at the ferried and anchor point interact. All this information helps us to design the connectors. Through this table, we can approximate pretension, satisfying the project specification, and also horizontal distance to maintain the tension, and also structural stability of the line. This becomes clearer if we plot the values here. This is the plot of the output we saw in the previous slide. Here, I plot three values. The dark green line shows the length of the line on the seabed. Blue line is the steepness of the line. This is the df over dx in the output. And the purple line here is the line tension at the period. This could be a pretension we want. All these are plotted against the horizontal distance. As we see, steepness of the line increases drastically once it is lifted. And the line tension, the purple line, shows a similar tendency with the decrease of the line steepness. What I mean here is, no one wants to design the line in this kind of region. The whole line is lifted and small movement causes a horrible line tension. Also, in this region, the line does not have a proper steepness to hold the vessel. So, we can expect that pretension and horizontal distance we need for the detailed analysis are somewhere in this region. You can pick the values from this region, then run the detailed analysis either in time or frequency domain with other parameters such as wind and wave. This is general usage of the command table. Let me move on to the next page. So far, we reviewed the command table, and the next command is the command move. Let me start again. The command move is to investigate the total restoring force in the system. To use this command, we first need to model a proper system, because this command uses the initial settings of all the lines in the system. Then, once we issue the command move, MOSES relocate the vessel with a specific step size until it reaches total distance specified on the command. At each step, MOSES calculates all the restoring force in the system and reports it. The syntax is similar with the table command, but it has two options. First of all, the option line here defines the direction the vessel will move along. TH here is the direction measured from global x-axis, positive global y-axis. So 90 degrees is the global y direction. Distance is the total distance of the movement. And here number is the number of calculation steps. So the step size at each step is calculated by MOSES, and it is the quotient of the distance and positions. The picture on the right shows how this option works. For example, if we specify 90 degrees for the direction and 20 feet for the total distance and 20 for the total position, vessel will travel 20 feet in global y direction with a step size of 1 meter. And we also can compute the variation of restoring force due to the rotation of the body with this minus rotate option. Here, EXCUR is the excursion from the initial position. MOSES relocate the system at this position. Then, vessel will rotate. And THINC is the increment of the rotation, and the number is the number of total rotation. For example, if we specify 20 for the excursion, MOSES will locate the vessel 20 feet away from the initial position. Then, vessel rotates at this position as specified. It gives us a restoring force report at each step. Now let's take a look at the output. This is the output of this command. The first part tells us the location of the vessel at each step. As you see, it moves in y direction with a step size of 1 meter. This is what is defined with minus line option. Next part reports the restoring force for each direction. Because the vessel moves in y direction, only Fy is being reported. The resultant is the magnitude of force. Then, maximum and minimum tension of the line are reported. The picture above shows the forces on the body. After the hydrodynamic analysis, we can simply get this kind of report with a single command. As you see, we can check the mean wave drift force here. It is around 200 kips in y direction. And we can match this drift force with the restoring force report in the table here. Then, we can approximate the offset from the initial position and also the line tension and the forces at the ferrite and anchor point in the system. Of course, after every calculation, you can plot the output like this. This is almost all about the command move. Next command is the command geometry, and this is the last command for the mooring design. What this command does is to simply returns the global coordinate of the points along the one mooring line. So we can check if there is any interference with the line and the other stuff below the mooring line. For example, if there is some pipelines under the mooring line, we can check the interference with this command. The table on the right here is the output of this command. As you see, coordinate of the line is listed against the distance from the anchor point. Also, we can plot the global G coordinate of the line. This command is very simple to use. Just type in the letters geometry and specify the name of the line to be investigated. This is all. Let me move on to the next page. Until now, we look at the three commands for the mooring design. Now, let me move on to the command for sling design. For the lifting analysis, the name of the command is sling_design. Let me start again. This command is to help the design of lifting slings. First of all, let me explain the syntax of the command. If you look at the second line of the MOSES command, here, a set of information is defined on the command. The first set of information is the node information the slings will be attached to. And the second information is the initial height of the hook point. Beginning height. And maximum height, the MOSES will finish the calculation. And third information is the number of calculation. Once the command is issued with this information, MOSES calculate the center of gravity of the cargo. Then virtually locates the hook point at the same horizontal location of the CG of the cargo, but different elevation here, as you see in the picture here. The beginning height is measured from the highest node on the command. Then connect the slings to that hook point. Then calculate the length of slings and the tensions in that configuration. After the calculation, MOSES relocate the hook point, then do the computation again. Here, the step size is determined from the beginning and maximum height, and the numbers defined on the command. Step size is the maximum height minus beginning height divided by number of steps. MOSES repeats this process until the hook point reaches the specified maximum height. Let's take a look at the output of this command. What I defined on the command is the four corner node of the jacket as shown in the picture here. Then I got the result below. First of all, if we look at the first column, here the height starts from 149 feet and finishes 349 feet. This is because initial and maximum height are measured from the highest node defined on the command. G elevation of the highest node is 49 feet from the water level. Then beginning height is 100 feet. It's added to this number. And the results are reported every 5 meters. This 5 meters is step size. As you see, in this configuration, the line attaching to the node J09 shows highest tension. Then the tension decreases as the hook point goes up. And also, as you see on the right hand side, you can plot the line tensions of all lines against hook height. You can also plot line tension versus length of the line here. So we can visually check the impact of the hook height under the specific sling configuration. Once we get this kind of report, we can change the configuration of the slings, then get the report again. Because this does not need heavy calculation, the analysis is very light and quick. What I mean is, I change the joint which the lines are attached to, then get the report again to see how things are changed. As you see, the tension gets higher than the previous and increases as the hook goes up. Definitely this is not a good configuration. And also we can plot these kind of things. This is almost all about this command. Let me move on to the next page. We took a look at the sling design command, and now it's time for the thruster design. The name of the command is propmax. Let me start. This propmax command is used to obtain an envelope of maximum wind, current, and wave, which yield one propulsor unit having maximum thrust. For example, let's assume that we have this kind of system. The green box represents the vessel, and the letter P at the corner of the vessel means the location of the propulsor, which applies the thrust force to the vessel. So it has total 4 propulsors in the system. To use this command, we need to define the environment first for MOSES to use. So it is defined before the command. As you see, wind, wave, and current are defined, and their direction is shown with the green arrows on the right hand side. Now let me explain how this command works. Once this propmax command is issued, MOSES fixes the current and wave profile to the initial value defined in the input file. Then increment the wind speed with a specific step size to find the maximum wind. During the incrementation, MOSES calculates thrust force to hold the vessel at the position against the applied current, wave, and wind. We can think this is a series of static equilibrium analysis to find the thrust force to remove the residuals in the system. Once one of the thrust force reaches its maximum, MOSES stops incrementing wind speed and reports that wind speed as a maximum wind speed for that heading. Then MOSES rotates the vessel and goes through the same process to find the maximum wind speed for this new heading. MOSES repeats this process for all 360-degree headings with a 10-degree step size. Once we found the maximum wind speed for all headings, now it's time to find the maximum current speed. This time MOSES fixes the wind speed and wave profile to the initial value defined on the &EMB command and increment the current speed, and go through the same process to find the maximum current speed. After finding the maximum for one heading, MOSES rotates the vessel, then repeat the computation for all headings as it does for the wind. Now it's time for the wave, and MOSES follows the exactly same procedure for the maximum. Fix the current and wind to the initial value as defined in the CIF here, and increases the wave height until one of the thrust force reaches the maximum, and repeat the process for all headings. After the calculation, MOSES gives this kind of report to us. As you see, maximum environments are reported for all headings. Also, we can plot these values here. From this report, we can approximate the maximum thrust forces we need under a specific environment. This is all about this propmax command. Let's recap the commands we have looked at today. First of all, there were 3 commands for the mooring design. Here, the command table and move are to get the mooring line stiffness table and restoring force in the system. To set the initial configuration of the mooring. And with this command geometry, we can get the global coordinate of the mooring line for the interference check. As for the sling design command, we can get the report of needed sling length and the tension against the various hook elevation so that we determine the configuration of lifting slings. And this propmax command returns the maximum environment profile to make one thruster exert maximum. All the calculation of this command allow us to do the parametric study without heavy calculation. I mean, we can save much time. This is all I prepared today. Thank you very much for your listening. If you have any question, please send me an email. My email is listed here. Thank you again.